Okay, welcome back. Today we're going to take what we've learned about implicit differentiation and we're now going to apply it as we talk about related rates. As we read here, related rates occur when two or more time-dependent quantities are related by some equation. Then their rates of change with respect to time are also related. And we can actually find those by using implicit differentiation. So, for example, if you had let's say, a rectangle here or a square here, then the area of that square is related to the length of the sides by the equation area equals x squared. So if we were able to take our square and grow the sides by some amount, obviously, couldn't do this with a real physical object. Well, we can do it as an imaginary object, or what I can actually do on my screen here is I can grow things. So keep increasing the length at some constant rate, that x is related to time. Then the area is also going to be changing and be related to time as well. And so that's what we're talking about when we say two time-dependent quantities. If you wanted to make it a rectangle where you had x and y, then area would be related to x times y. And as you change x or y, they could be related. Or we could talk about the perimeter around the outside. Perimeter would be 4x. How does that change as x changes? Or we could even get in and say, what about the length of the diameter? How does that change as x changes? So those are just different things that could all be connected back to x and how x changes. And so relate involves that relationship there. Involves that relationship. If I can get onto the right pen here. Involves that relationship. And we can find a relationship between the rates of change of a and x by differentiating. Okay, so that's called a related rate. We're going to now turn to an example here. So let's take a look at this problem here. A spherical balloon has air being pumped into it at a rate of 4 cubic centimeters per second. We want to know how fast the radius is changing when the balloon has a radius of 10 centimeters. So the idea is we have a balloon, and unlike the balloons you buy in your store, our balloon is always a sphere, no matter how much air it has in it. So it's perfectly elastic, and we can make it as big as we want. Right? We can have a 10-mile radius balloon if we want to pump enough air into it to get it to that. Right, so our balloon's a little bit different. It's a theoretical balloon, but a regular balloon would work. You'd have to have enough air in it to have it all ready to its spherical shape, and as you continue to blow more air into it. Okay, so here's our situation. First of all, how are volume and radius related? Well, it's a perfect sphere, so we know. Well, first of all, let's write down what I know. dV/dt is 4 cubic centimeters per second, right? That's the rate the volume's changing at. And we know that volume is 4/3 pi r cubed. Right? That's one of our formulas for the volume of a circle. 4/3 pi r cubed. And now we want to find the rate that the radius is changing at. In other words, we want to find dr/dt. So we begin this problem by performing differentiation with both sides with respect to time. So we don't know what the starting radius was at any point in time. We just know that, or what the starting volume is. We just know that the volume is growing at a constant rate of 4 cubic centimeters per second. And we want to see what effect that has on how the radius changes. So we differentiate here. And when we differentiate, we get dV/dt equals 4 pi r squared, right? 4/3 pi, and then we would multiply by 3, so the 3's would cancel out. We get 4 pi, drop it by 1, r squared, and because of implicit differentiation here, we're differentiating with respect to time, so that would be dr/dt. And so that's what we want to find. How is the radius changing. What is d r dt, in other words? So we can take that expression and we can solve for d r dt. So get everything that's not d r dt on the other side. Do that by dividing by it. So we get dv dt over 4 pi r squared. 4 pi r squared. So first thing I want you to notice here is dr dt is not constant. In fact, dr dt is actually dependent on what the current radius is. And that should make sense if you give it a little bit of thought. If you have a very, very small balloon, then 4 cubic centimeters, maybe the volume of your balloon's like 1 cubic centimeter at the start. And then we've added 4 cubic centimeters. That's going to be a huge increase. But if our volume is already up to like 400 cubic centimeters, another 4 is going to be a very small change in the volume, which will probably correspond to a relatively rather small change in the radius at that point. So the bigger the radius is, by a factor of r squared in this case, that's going to contribute to dr dt. So we were told in the problem the radius was 10 centimeters. We were told dv dt was 4. So let's plug that information in. And then we can work that out. We get the dr dt is 4 over 4 pi times 10 squared, which gives us a gives us a rate of change of 0.0032 centimeters per second. So it's growing very, very slowly at that point because we already have a lot of volume in that. Right? If you put 10 centimeters into your volume formula, you'd have 4/3 pi times 10 cubed, which would be 1,000. So 4/3 times pi times 1,000. Well, you can estimate that at around 4,000. It's actually going to be a little bit bigger than 4,000, but it's already huge. So an extra 4 cubic centimeters doesn't really contribute much when we already have over 4,000 cubic centimeters in the balloon. And that's why the radius growth is very, very small relative to that current 10 centimeter radius. Okay, so hopefully this helps you as we get started here with these related rate problems. They are ones that typically give a lot of people trouble, so please work on them. Be careful with them. Try to be patient with them, and maybe try to work through these examples along with me. It might help you as well.